Okay, on this video we are going to continue with exact differential equation, but in this video we are going to know how to recognize if it is an exact differential equation. Okay, first of all, remember the concepts that we saw in the previous video, the three concepts. And now let me define what is the shape of the exact differential equation. This is the shape of the exact differential equation. Something that is function of two variables times the differential of x plus something that is function of two variables times differential of y equal to 0. Okay, the m, we define here the m, capital M here, and we define n, capital N here, but here the rule is that the m always goes with the differential of x and the n always goes with the differential of y, according to the book. Okay. Now, why this is taking this shape? Because in theory, an exact differential equation comes from a differential of an exact function. And here is the differential of an exact function, alright? Because it's an exact function, it is equal to 0, so the differential is equal to 0. Okay? So here is the partial of f respect to x and the partial of f respect to y. So that means that the m is equal to the partial of the function respect to x, and the n, capital N, is equal to the partial of the function respect to y. Okay, now, having the shape in this way, it doesn't mean it is exact differential equation, right? So what we have to do is a test. The test that we have to do is to check, so let me write it here, to be an exact differential equation, this shall happen. What shall happen? It shall happen that the partial of the m respect to y must be equal to the partial of n respect to x. Now be careful here. The m goes with the differential of x, but here you are taking the partial respect to y. And here the partial of m is respect to x, even though here you have the differential y. Now, why we have to check this? Because if you replace the value of m and n that comes from the partial of the function, then this should happen. The partial respect to y of the m, and the m happens to be the partial of the function respect to x, equal to, on the other side, the partial of n respect to x, the partial respect to x of n, and n is supposed to come from the derivative respect to y of the function, partial of the function respect to y. So what happens here is that this is a second partial derivative of the function, first respect to x and then respect to y. And on the other side, it is a second partial derivative of the function, first respect to y and then respect to x. And this reminds me the second concept we saw in the previous video. Here you have the cross partial derivatives, and they happen to be the same. And because they happen to be the same, if they happen to be the same, then the m comes from the partial of the function respect to x, and the capital N comes from the partial of f respect to y. So with this, you ensure that it comes from a differential. So with this, you ensure that this comes from a differential, alright? Otherwise, if it doesn't come from a differential, then you cannot solve it, alright? So let's do one example. For example, let's say like you have this differential equation, 2xy differential of x plus x squared minus 1 differential of y equal to 0. Let's say that you happen to have that differential equation, because in these exact differential equations you are given this as the problem, alright? They don't give you the exact function, because actually the exact function, the original function, is the solution. You are given this. So from here, the first thing to do is to identify what is m and what is n. So this one is the m, x comma y, and this is the n, x comma y. Why? Because the m goes with the differential of x, and the capital N comes from the differential of y. Okay, now what you have to do is to do this test. So let's take the partial of m respect to y. So the partial respect to y of 2xy. Because it is a partial derivative, then the x is a constant, so the derivative of this is just 2x. Alright? Now let's do the partial derivative respect of n, partial of m with respect to x. This one respect to x. Derivative respect to x of x squared minus 1. So the derivative of this is just 2x, and the 1 is equal to 0. Okay? So as you can see here, these two are equal. Because that is equal, then that means that this comes from exact function. Alright? So this is just to test if it is exact. So again, just because you have the shape of the exact differential equation doesn't mean it is an exact differential equation. You have to check this. Alright? Okay, let's do another example. I'm going to make up another exact differential equation. Okay, let's say that you have the sine of xy differential of x plus, let's say you have exponential x exponential y differential of y equal to 0. I just made up that problem. Okay, according to that, this is my m and this is my n, alright, of two variables. Okay, let's do the checking if the partial are the cross partial derivatives are the same. So let's do the partial of m respect to y. Derivative of this respect to y. Derivative of the sine is the cosine of xy. Derivative of this respect to y is just x. And then the partial of n respect to x. Derivative of this respect to x, because the exponential of y is a constant, then it's going to be just exponential of y. Now they happen to be not equal, then it is not exact differential equation. Because it's not exact differential equation, then you have to use another method to solve this differential equation. But for this one, it is exact differential equation, and then we can solve it. All right. So again, just because it has the shape, this one has the shape, and this one also has the shape of an exact differential equation, it doesn't mean it is exact. It has to comply with this property. Why it has to comply with this property? Because it is the second partial derivative cross-check, and they happen to be equal. If they happen to be equal, then it means that this comes from a differential of an exact function. Now, this is not exact, then this is not, it doesn't come from the differential of an exact function. Just let me add here the differential of a function, differential of a constant. Therefore, the differential of a function of two variables is this, and the differential of a constant is equal to 0. All right. Now, this video is just to check to know if you happen to have an exact differential equation. On the next video, we are going to make the solution of an exact differential equation. And actually, let's try this one in the next video.